Welcome back, engineers. We are discussing common techniques and algorithms in system design, and in this video, let's learn about B trees and B plus trees. Now, I want to split this into a two-part video. In part one, let's try to understand hard disk internals. We'll see how data is stored, how files are accessed, and how database tables, when they are stored on disk, are accessed with and without index, right? So let's try to understand all this in this video, and in the next video we'll try to cover what is a B tree, what is a B plus tree, and we'll see how that actually reduces the amount of disk reads that we need, and that creates efficiency. And we'll see why this is such a favorite among SQL, NoSQL databases like MongoDB, among file systems and storage systems, right? I hope you're ready. Let's get started. So in this video, let's try to answer this question. Where is my data? So a typical hard disk would look something like this. So there's a hard disk and data is sitting somewhere here. So let's say I have a table like this with some columns, ID and code, and let's say there are some rows, and I want to know where this data is placed in the hard disk, right? For that, let's try to understand a little deeper how a hard disk is structured and how data is actually managed there. So let's say this whole hard disk is like an entire city, and this is my house, right? So if I have to go to a house, I need to know some kind of an address, right? And addresses are given by partitioning the city in some way, right? So hard disk is also partitioned in such a way. So the platter on the hard disk that we have seen before, this thing is called a platter. The circular disk is called a platter, and it is partitioned in concentric circles like this, and each circle is called a track. So these are logical circles and not physical circles, and each of them is called a track, right? So my data could be lying anywhere on any of the particular tracks. Now, is this division enough? No, we need further subdivision. So we break down these circles as well into smaller bits using something called as sectors. Now we go across tracks and we divide them into sectors like this. This is one sector, this is one sector, this is one sector, and so on, right? So as the disk is spinning, this arm is lying over the disk and it is trying to access different parts of the circle, and depending on the sector it is in, we can see that data is residing in different tracks and different sectors. So now we have reached two levels. We know what track our data is in and we know what sector our data is in. We can do further division, and this is how it looks like. So now we know the track and now we know the sector. So within the sector we can see there is further subdivision, and this blue section is called as block, right? This is where our data is actually residing, and each block is typically 4 KB of data, right? Which is around 4000 bytes. So I'm keeping it to round figures for our easier calculation. This video involves a little bit of math, so just try to stay with me. I've tried to reduce the numbers to easy multiples for our easier understanding. So just stay with me. I think it will be clear to you by the end of the video, right? So each block is having 4 kilobytes of data, and there can be multiple such blocks like this in a sector, right? So this is where our data is lying. So if you want to answer the first question, where is my data on the hard disk? Now we have an answer. So our data point was here. There's this white dot. Let me make it green and bigger so that we can see it. Now that we know how our hard disk is laid out, we know the layout of the city, so we can actually get an address, right? So let's see how that looks like. So let's say our tracks are numbered like this, 1, 2, 3, right? So these are my tracks. Now let's see how my sectors are numbered. So these are my sectors, 1, 2, 3, 4, 5. And within the sector, I can have blocks like this, 1, 2, 3, right? So in order to answer the question, where is my data? Now I have an address, track 3, sector 1, block 3. So we go to track 3, which is this outer circle, right? And within this outer circle, we go to sector 1, which is this part. And within that, we have to go to block 3, which is here. So now I have found my data, and similarly there will be a mapping maintained for every file, and every file will have some kind of a block assigned to it inside the hard disk, and that's how we know where to go and access the data, right? So let's see how that looks like. So this is the typical RDBMS system. Let's say there is some metadata in some form maintained by the RDBMS system, and it is maintaining some tables, let's say user table and order table, and it is maintaining that which table is in which file, the mapping between table name and the file name. So it can be .db, .dbf, whatever it may be, depending on the database being used. So it is a pointer to some kind of a block inside the hard disk, right? So this is the hard disk, and we are looking at blocks assigned to this particular file. So the blocks can be sequential like this: block 1, block 2, block 3, block 4, block 5, and so on, or it could be random: 44, 56, 32, 37, and so on, right? Depending on the availability, it will try to get sequential blocks. Otherwise, it will need to make use of whatever blocks that are available, right? And this is a mapper to show that this file is having these many blocks allocated to it, and operating system or file management system can know where to go and look for it, right? So if I want to go through the user table, I know that I can come to here. This is the starting point, block 1, and now I can go to all these blocks and traverse through it, right? So let's say somebody is doing a query find by ID. So I want to search the entire table for that particular ID. This is how a system would do it. It will go to block 1, block 2, block 3, and so on in a sequential manner and try to complete the whole file, right? So this is how data is accessed in a hard disk. Now let's try to understand how many blocks of data do we need to store these many rows, right? So if we look at it, every row is having 10 bytes of data requirement. So this is integer 4 bytes, and then these are 6 different characters, let's say a total of 10 bytes, right? And there are 10 such rows. So taking a total of 10 into 10, 100 bytes. So before we go any further, I want to take you to a world that is different from our regular time complexity analysis. We are talking about disk access and disk access efficiency with this video. We are not talking about our typical time complexity when we are putting stuff in the RAM and we are trying to analyze how many access points do we need, or what is the time complexity and space complexity for those data structures. We're not doing that. We are actually talking about physical reads on a hard disk here, and our aim is to reduce the number of disk reads required to do any operation, so that if the disk reads are less, our performance will be higher, right? That is the aim that we're trying to do here. Okay, let's begin. So let's see how many blocks we need. So one row requires 10 bytes, 10 rows requires 100 bytes, and we know that one block is having 4000 bytes, approximately 4000 bytes. So what will be the number of blocks required? 100 bytes divided by 4000, which will be around 0.025. So one block is enough. So in just one block, we can fit 10 rows. Since it is a small data set, one block is fairly sufficient to do this input, right? So let's try to scale it up now. So if we scale it up to 1 million rows, right? It is a very common thing these days to have 1 million records in a database table. So let's say we have 1 million rows, and each row has a requirement of 10 bytes that we have seen before. So a total of 10 to the power of 7 bytes is what we need as a data storage requirement. So how many blocks do we need? Again, we'll do the same calculation. 10 to the power 7 divided by 4000. This will give us 2500 blocks to store 10 to the power of 6 data points, right? Now let's see how much time is taken for doing a linear search. We have not introduced any index yet. So if we want to do a find by ID, the DBMS system will have to go through block 1 and continue to read all the blocks, right? And we have 2500 blocks to read. Now we know from our previous video that when we discuss numbers, we talked about latency numbers, and we know from here that if you see here, read 1 megabyte of data sequentially from disk, it will require about 30 milliseconds. Just take that number and come back here. 1 megabyte will require 30 milliseconds. And we have how many megabytes? Let's convert it. 10 to the power of 7 bytes, I'm going to divide it by 10 to the power of 6 to get a total of 10 megabytes. And we have 1 megabyte 30 milliseconds, so 10 megabytes will have 300 milliseconds, right? 300 milliseconds is required to read 2500 blocks of data. So if you are doing find by ID, it is doing a linear scan for the entire table, and it will require 300 milliseconds to do one search, right? Which is a huge number. So let's try to optimize this one. We will introduce an index table. So here's what we'll do. Index table is also residing on the hard disk, but it is acting as a pointer to the main table. So this is how it goes. So for an index table, we'll have two columns. One is the ID column, which is directly coming from here. We will have all the entries from here, in the ID column over here, right? And then we have a location pointer, which is pointing to some address of this row, right? Some disk address of this row. We've already seen how that address looks like in the previous section, right? So this is ADDR1, this is ADDR2, and so on, right? So this is how we build a typical index. So this is also in the hard disk. It is also occupying a few other blocks, but it will give us some advantage. So let's try to analyze that. So in this case, we have 10 to the power of 6 entries in the index table as well, along with the pointer to the main table. So let's see what happens now. So now let's analyze the number of blocks required to store the index itself. So we have 10 to the power of 6, and each row will require 5 bytes. So this is the storage requirement for 5 bytes. I kept it as 5 bytes for easier calculations. So let's say we need 5 bytes. So how many total blocks do we need? This divided by 4000 bytes, which will be exactly 1250 blocks, which is like half the number of previous blocks that we have seen before, right? So in order to do a search now, here is what we'll do. If we want to do find by ID, we come here, we do a linear scan on this one, right? And once we find something, let's say my ID is 3, once I find it, I know where to go to get the address 3. I directly go here and fetch the record and return to it. I don't need to do a scan of these 2500 blocks of data, right? So my search space has now reduced to 1250 plus 1 block to access the main database table, and a total of 1251 blocks is what I need to do a linear scan with index, right? So from 300 milliseconds, now I have brought down the search time to 150 milliseconds, right? This is the time taken for linear search now after introducing the index, right? Can we optimize it further? Let's see. Let's introduce another index, an index of an index. So here is what we'll do. So first time when we built an index, we took all the rows from here, all the IDs, and we built a location pointers to the main table, right? And if there are 10 to the power of 6 here, there will be 10 to the power of 6 here, right? And this also is occupying a disk storage, right? So how do I build an index for this one? So do I need to do 10 to the power of 6 again? No, let's try to do a little smarter way and see if we can reduce the number of blocks required to store this index, right? So in order to build the second index, what I want to do is I want to calculate how many rows I can store per block, right? Let's see how that goes. How many rows per block? We know that one block has 4000 bytes, right? And we know that every row requires 10 bytes. So how many rows can we fit in one block? 4000 by 10, we can fit about 400 rows in each block, right? So here is how we will use this information. To build the second index, I will only keep track of the number of rows per block. So in the first row, I will keep track of 1 to 400. So if there is any entry required between 1 to 400, I will send it here, right? And from 401 onwards, I will send it to someplace else down here. Let's say this is my 401 entry. So the segment 1 to 400 will be pointed here. The segment 401 to 800 will be pointed next. 801 to 1200 will be pointed next, and so on, right? So for every 400, I will have a pointer here. So I am reducing the search space from 10 to the power of 6 to 10 to the power of 6 divided by 400 basically. So I am doing like this. This is one block, this is one block, this is one block, and so on. So like that, I am able to reduce the number of search spaces. So let's see. So as a total, here we will have 2500 entries compared to 10 to the power of 6 entries, right? So depending on the input, let's say I'm getting an input of 1024, I know that which block will essentially have this. I will directly point to that address, and from that I can do a small scan, and then I will take it higher to this guy, right? So in simple couple of steps, I'm able to jump to my data point and reduce my search space. Now let's see how many blocks are required to store the second index. Now we know that one row requires 5 bytes of data because it is the same structure as before, one ID column, one data pointer column, and we have 2500 rows. 2500 into 5 will give us 12500 bytes. That is the number of bytes we require to store this index table, second index table. Now let's see. Number of blocks required is 12500 by 4000, which will be about 3.125, close to about 4 blocks. So we just need 4 blocks to store the second index, right? So now comes the magic part, right? How to do a search now? In order to do a search, we just need 6 blocks. How? Let's see. So when we're doing a search on the second index, we know that worst case requirement would be to search for 4 blocks in this. But once we have that, we know exactly where we need to go in the index table, and we will do a scan about 400 rows, which will fit in just one block. And once we have that, we will actually go to the data point and we will get the actual data, which is again accessing another block, right? So a total of 4 plus 1 plus 1, 6 blocks of search is required to do a linear scan using 2 indexes, right? So in just 6 blocks, we can do a quick scan to reach our data point. And what is the time required to do this? We have 6 blocks, so each block will have 4 KB. So converting this into megabytes, we now have 0.024 megabytes, which will give us about 0.72 milliseconds, right? And that's all we need to do an entire linear scan on a database table with couple of indexes, right? So we've brought it down from 300 milliseconds to 0.72 milliseconds. So that is the magic of using multi-level indexes, and that is how we can reduce our number of disk blocks required to be read in order to reach a particular data point, right? So the question remains is, who will build this index, right? So I've added one index, I've reduced the search space to half. I have added another smaller index, I have reduced the search space to a greater index. I can add one more level, I can add another level to reduce it even further. But who is actually going to do it? And our databases are constantly changing. Data will grow, data will shrink depending on the requirements. I want this whole process to be automated. I don't want to do it manually. I want this whole process to be automated. The system should be smart enough to detect when there is more influx of data, that it needs to add more layers to it. And I want the system to be able to automatically delete stuff and reduce the number of indexes when the data is actually shrinking, right? So that is the power of B trees and B plus trees. And in the next video, we will cover that. So I hope from this video you got the basic intuition behind hard disk internals and how data is accessed from disk. And in the next video, we'll try to cover the remaining topic. Until then, thank you so much for watching. I will see you in the next one. Cheers.